Welcome to the video. In this video, we are going to look at problem number 25 of chapter 22, and we are going to solve the problem from scratch. From the diagram, you can see that we have three arcs, each carrying different kinds of charges. Our assignment is to calculate the net electric field at the origin. Let's first observe that there is a symmetry built into the problem. This symmetry is a mirror symmetry, and the line of symmetry, which represents a mirror surface, lies along the northwest-southeast direction, as you can see here. What this means is, on either side of the symmetry line, if there is a charge element on one side, there will be a charge element on the other side. What you want to do is to choose a coordinate system that takes advantage of this symmetry. This is an important math tool. The textbook touched on it back in chapter 3. And you can find it on page 51, where they talked about rotating the coordinate axis to suit the problem. Some of you are going to move on to courses like Advanced Mechanics and Quantum Mechanics. In those courses, symmetry and coordinate transformation are done all the time. In this example down here, you can see that they rotated the x and y coordinate system, and the new coordinate system are labeled x prime and y prime. In our case, we are going to choose the line of symmetry as the x-axis, and this can be done by rotating the diagram counterclockwise by 45 degrees, so that it looks like this. And you can see that once this is done, there's virtually no difference between this diagram and the diagram in sample problem 22.4.1. The only differences are that the diagram appears to be flipped, and also the angles are different. In the sample problem, we have two angles, each 60 degrees. In the current problem, we also have two angles, each is 45 degrees. Despite these differences, the way to solve the problem is really just the same. So we are now going to look at this second diagram on the screen. And let's now look at the smallest arc. And for the moment, forget about the other two arcs. The first step is to calculate the linear charge density, which is the total charge divided by the total length. For now, we'll just say that the total charge is the lowercase q, and from the diagram, we can see that the total length is just a quarter of the circumference. Or you can use the definition for the arc length to do the calculation. And here, the angle theta is a quarter of 2 pi. Of course, you can do it either way, and the result will be the same. The second step is to do a partition and divide the arc into small pieces. Each piece will carry a charge of delta Q, which is equal to lambda, the linear charge density, multiplied by dl. Notice that in the expressions that we have so far, L and S mean the same thing. And from the definition of the arc length, we can obtain expression for delta L or delta S. And we can do a substitution so that delta Q is written in terms of delta theta. The electric field created by the delta Q can be easily calculated using the equation that by now we are familiar with. Notice that we have a cancellation in that last expression. In addition, since there is some symmetry, which means for every element that we looked at, there's one on the opposite side, so that the opposing components will cancel each other. And the surviving component is the component with the factor cosine theta. And therefore, the magnitude of the delta E is equal to K, followed by lambda delta theta over R, and followed by cosine theta. And this expression is true for every element that we care to look at, which in turn means that we have a total of n elements, and we need to add them all up for the net electric field. But this is only an approximation, because that equation works only for a point charge. In order to get the real value, we need to take the limit. After we take the limit, we will see that the expression can be represented by an integral, where the original limit and summation signs will be replaced by the integral sign, and the starting and ending indices will be replaced by the integration limits, which in the current case will be equal to negative 45 degrees and positive 45 degrees. In addition, it is important that we recognize what the integration variable is. It will be the one that is associated with the delta, and we'll replace the delta theta by d theta. This is an important step because what is left will be the integrand function itself. And since k, lambda, and r are all constants, we can move them out of the integral. And we have arrived at an expression that looks like a Calc 1 integral. The integration is easy and straightforward. Since the sine function is an arc function, the sine of negative 45 degrees is equal to the negative of sine 45 degrees. And we will arrive at the final expression. That is the electric field created by an arc at the center of the arc. And of course, we have a total of 3 of them. It is now ready to plug in the numbers for each case. Let's look at the numbers for the first arc. For the first arc, the total charge is positive Q, uppercase, and the length is a quarter of the 2 pi r, uppercase. And therefore, we will have this expression for the charge density for the first arc. Notice that even though in the expression on the right hand side there is a positive sign, later in the calculation I will use only the magnitude. And for this first arc, the radius is uppercase R. And now we are ready to plug in term by term. Let's first plug in the expression for the linear charge density. And once again, notice that I am including only the magnitude and not the sign. And that should be followed by 1 over R. And in this case, that R should be an uppercase R. And then that will be followed by 2 times sine of 45 degrees. And since for the first arc, the charge is positive, the resultant electric field should be pointing away from the charges. And because of the symmetry, we can conclude that the direction of the field created by that first arc will be horizontal to the right. So let's add the vector sign to the existing expression. Moving on to the second arc, let's first calculate the linear charge density. In this case, the total charge is negative 4Q, and the length is a quarter of the circumference. But notice that this time, the radius is 2R. And notice that we again have an expression that has a sign in front, this time a negative sign. But when we are ready to plug in, we will use the magnitude only. And for this second arc, the radius is 2R. And we are now ready to plug in the expressions. And once again, we will do it step by step. First, the k, and followed by lambda. And then this will be followed by 1 over lowercase r, which after plugging in will be equal to 1 over 2 uppercase r. And then that will be followed by 2 times sine of 45 degrees. And after a bit of algebra, we will find out that the expression is actually the same as before. Since for the second arc, the charge is negative, the direction of the electric field should be horizontal to the left. The calculation for the third arc will be done the same way. Notice that for the third arc, the radius is 3r. And after a bit of algebra, you will see that for the third arc, the magnitude is still the same. And because the charge is positive, the direction of the resultant electric field will be pointing horizontal to the right. So we now have 3 electric fields, including both the magnitude and the direction. And we are now ready to do a vector sum for the net electric field. And because all 3 electric fields have the same magnitude, and that magnitude can be moved to the front when we do the vector addition. And we still have the unit vectors, so let's do that in a parenthesis. And of course, that negative sign in the middle comes from the electric field for the second arc. And the result is just a single I hat. And that is almost the expression for the final electric field. The magnitude is correct. However, we will notice that this I hat is the direction in the transformed coordinate system. And let's draw that. And we have to move that back to the original coordinate system. And in that original coordinate system, the direction of the net electric field is along the southeast direction. Or in the book, they will call it negative 45 degrees. So there we have it. The magnitude of the net field is shown at the bottom of the screen, and the direction of the field is shown at the top of the screen. You can use the expression at the bottom of the screen for the calculation of the magnitude, and the direction will be described as having an angle of -45 degrees. And that completes this video.